Welcome to Brain Vision.
Okay, so we have some information about a hammerhead in this problem. We know its weight is 4.9 newtons. We know that it comes down and hits a nail with an initial velocity, so this is downward, so that's why it's negative 3.2 meters per second, and then the interaction with the nail brings it to a halt. That will give us final velocity of 0, and then the nail decompresses into the board, 4.5 millimeters. So we're just going to go ahead and convert that into meters right off the bat so that we have it in SI units. And then in addition, the person, you are applying an applied force of 15 newtons. Okay, so we're drawing a free body diagram for the hammerhead in part A. So that's our hammerhead, nice and square. There are two forces acting in the downward direction and then one force acting upward. So those are the weight and then the applied force respectively. Probably should have drawn the applied force a little bit longer because it's 15, whereas the weight is about 5, but that's okay. Moving on to part B, we can turn this into a solvable equation using Newton's third law. So that is, F is equal to ma, but F is really the sum of the forces. That's normal force minus the weight minus the applied force is all going to be equal to ma. What we really want to know is what the normal force is, because that's the force that the nail exerts on the hammerhead. So we can just isolate that first equation to solve for the normal force. So all positive terms. And that's great and all, but we don't know what the acceleration is. So we're going to have to use a little bit of kinematics in order to solve for that. So based on the information given to us, we should use the equation with the velocities squared. That's this equation in order to solve for acceleration. Oh, and then we know that the final velocity is 0, so we can set that equal to 0. We're going to do negative v naught squared over 2 delta y. Plug in numbers, lots of negative values because everything is acting downward. 2 negative 0.045, really small displacement. And then we get an acceleration of a very high number, 1,138 meters per square second. I'm just saving a couple more significant figures than I probably should be because that's not our final answer. And then we can bring this down and then solve for the normal force by plugging in all the numbers that we know. So we don't actually know the mass, but we know how to solve for it by dividing weight by gravity. So that's the mass. Multiply that by the acceleration. Add that to the weight again, so that's 4.9. And then adding that to our applied force of 15. Plug it all into a calculator and then get a value of 590 newtons to two significant figures. Good. And then we also have a part C where we are wondering if the vertical displacement was instead 12 millimeters, sorry, 1.2 millimeters, then what would the normal force have to be instead? Sorry, meters. So we use the same equation that we just derived. That's the one with the acceleration, 2 delta y. So the velocity is still the same. but the displacement is just different. So plug that in here. So the new acceleration is much higher, 4,000. And we'll see how that affects the normal force. It's the same idea. Divide weight by gravity, then multiply by acceleration, and then add it to the weight and the applied force. Plug and chug into a calculator and then get 2,200 newtons.